So today I'm going to go over the second part of Chapter 9, Comprehension Check Questions. The first part of Chapter 9 introduced you to solutions and I hope a few terms that you're familiar with of solute and solvent, saturated and not saturated solutions. So now in this part of the chapter, we're going to actually concentrate on concentration. And so concentration is something you've probably been a little familiar with. You just maybe have not used appropriate terms. You see it when you're younger and you're having, say, a juice or a lemonade. Sometimes you get it and it has a very strong concentration. It's really tart and it may make you pucker funny. Or you can get it lemonade sometimes and it's really weak and has a very low concentration, which means it has a very low amount of lemon and sugar and it tastes very watered down, right? So in chemistry, we deal a lot with concentrations, and the reason we deal with concentrations is a concentration can actually affect how a chemical behaves. And so we measure concentrations in two main ways. So I wrote them down. So the two main ways that we measure concentration is molarity, and I've written molarity with a capital M because a capital M is actually the symbol that we use to demonstrate that we've calculated molarity. And so a molarity for this concentration is the moles of the solute, which a lot of times is, a powder that you've massed out. Now you don't mass it out and get the moles. You have to calculate that using the molar mass from your periodic table. And it's over the liters of the solution that you're making. This kind of tricks people because a lot of times our book will try to give it to you in milliliters. And then the other type that we're going to use is molality. And I wrote it with a little m because that's the symbol that we use for molality. And molality is very similar. It has the moles of the solute is the same. But for molality, we're not dealing with the volume like we are here. We're actually dealing with the mass of the solvent. So like what is the mass of the water of your lemonade that you're using? So these are the two main formulas we're going to use for this set of comprehension check questions. I'm going to put that up here just so that we have it. And if you haven't learned them, write them down and keep them nearby because you're going to come back and want to know those. Question number 5 tells us that a student measures out 15.67 grams of ammonium carbonate. And you dissolve that into enough water to make 200 milliliters of solution. And the question asks us, what's the molarity? So there's a couple of things that come to mind when I hear this question. One is, what is ammonium carbonate? And so this is where we have to take our knowledge from past chapters and apply them. So let's write down a formula. I'm hoping you haven't already forgotten that ammonium is a polyatomic ion with a +1, and carbonate is also a polyatomic ion. So when I'm writing my formula for ammonium carbonate, I remember that ammonium is my polyatomic ion that I've had to learn that has a positive charge and it's +1, and carbonate has a -2. So I'm going to crisscross my charges to balance that out. So I actually have 2 ammoniums. So now I know even what I'm talking about. I'm going to add this to a solution to make a 200 milliliter solution. And a lot of times people say, well, what do you mean? Why don't you just measure out 200 milliliters of liquid and then add it to it? Well, what actually happens is when you have 200 milliliters of liquid and you add your 15.67 grams to it, you would actually see your volume of your liquid go a little bit over 200. And so the goal is to only have a total liquid volume of 200. So that's kind of why it's written a little bit funny like that. And so we're asking for the molarity, which is moles of solute over liters of solution. So I need 2 things. I need to know the moles and I need to know the liter. I know the liters. I can figure that out really easy from 200 milliliters. But I don't know the moles. And so of course, back to good old stoichiometry here, I have my grams and I'm going to convert it to moles. So I'm going to put moles on the top. So put grams on the top and moles on the bottom. And first I have to calculate what is the molar mass of ammonium carbonate. And so if I were to take my periodic table and I'm going to add up all the parts of ammonium and multiply it by 2, and then all the parts of carbonate, I get 96.11 grams. And so grams cancel out, and I'm left with moles, which is what I was wanting. All right, so to find the molarity, I needed moles and volume. So I have those. So molarity and so I'm going to convert 200 milliliters to liters, which is 0.2. So I have moles over liters. And you end up with, and since this is molarity, you put a capital M. So comprehension check question number 6 is another molarity problem, but it's asking for basically a different variable in the equation. So we're going to take the same solution that we made in the previous problem where we took a sample of ammonium carbonate and we dissolved it into water. And we're going to take a known sample of 34.2 milliliters. So we're measuring out, probably using a graduated cylinder, 34.2 milliliters of this liquid. And my question wants to know, in that 34.2 sample, how many moles are there? And so we're going to look at molarity. So we know molarity. I know molarity is moles over liters. And I'm looking for the moles, and I know my molarity. I have it from the previous problem. It's actually 0.815. I don't know my moles. And I do know my liters because they give it to me. They just give it to me in milliliters, so I have to convert it. And so if you remember from chapter 1, there's 1,000 milliliters in a liter. And so I actually have 0.0342 liters. And I get, and I'm actually, I don't know if y'all remember, but when I do this, I frequently am using this method here. King Herod died, maybe drinking chocolate milk. And remember, this is meters, liters, and grams. These are our base units. And so this stands for kilo, hecta, and then deci, centi, and milli. And so if I'm going from milliliters to liters, I go 1, 2, 3. So it's 3 jumps to the left. So when I convert this to liters, I'm just going to move my decimal 3 jumps to the left. 1, 2, 3. And that's how I got 0.0342 liters. So then you're just going to calculate this through to solve for moles. So for your algebra, I'm going to have to multiply both sides by this. So I end up with 0.815 times point. So let me just rewrite it. Oh, I have pink. And that equals moles. And I can check my units because molarity is moles over liters, and liters will cancel out. And so when you calculate all that through, you should end up with 0.0279. And if you haven't already worked these problems on your own, I would strongly encourage you to either try it on your own or to stop it and pause it and try it, or to pause throughout the problems to just pause, work it yourself, and then double check my work against yours. Maybe you'll find a mistake I make. It happens. Question number 7. A chemist needs to make 450 grams of magnesium carbonate. So we're trying to make 450 grams of this. even if you don't have a clue what to do, I've already taught you that when you're stuck, if you have no idea what you're doing, you can always convert this to moles. But I actually have a clue as to what I'm doing on this one. So I'm wanting this to be my product. Now the question is asking me, it's telling me I have a 1.5 molarity solution. What volume do I need? I didn't write it down, but this solution is of MgCl2. So this is 1.5 molarity, which is moles over liter. And I am trying to figure out how much I need to start with. So like how much liquid do I need to start with so that at the very end, I get magnesium carbonate. So I only really have one thing I can start with, and it's going to be the 450 grams of magnesium carbonate, and I'm going to convert it to moles first, because that's what we do. Not sure if y'all can see pink as well. So 450. Go ahead and pause it and do this by yourself. I'm sure we're all really good at doing this work by now. As good old stoichiometry, you should end up with grams canceling out and 5.337 moles of MgCO3. So the next part, I can actually use my equation to go from moles of this to moles of this. Because I could write a ratio for this part of this problem, or I could just look at it, because this is one of those really nice equations where it is a 1 mole of MgCO3 reacts with 1 mole of MgCl2. So if I wanted to write the ratio, it would look like basically 1 to 1, and so moles would cancel out. So I'm running out of board space. So I also have 5.337 moles of MgCl2. Okay, I found that by going from grams of MgCO3 to moles of MgCO3, and then use my balanced chemical equation. I could figure out moles of this. Now, the next part is where we're really going to use our molarity. If you'll remember, molarity is moles over liters. So I have my moles. I'm going to fill it in. I don't have my liters. In fact, that's what the question is asking. What's the volume? But I do have molarity, because they told me that. So I'm going to rework this algebraically to solve for liters. So in algebra, I would basically multiply both sides by liters. And then this would cancel out. Then divide this by 1.5. And would divide this by 1.5. And since this is moles, this is molarity, which is moles over liters, moles will cancel out, and I'm left with my answer in liters. I hope I didn't lose you in the algebra on that. There are several different ways of reworking that problem. You do what works for you. End result is 3.6 liters. So at the whole thing, this is how much liters. So just to recap, we went from grams of magnesium carbonate to moles of magnesium carbonate. From that, we were able to use our balanced chemical equation to go to moles of magnesium chloride. And then we were able to use the molarity of the solution to calculate how many liters it would take to have that many moles. So if I was to take and measure out 3.6 liters, I would have in that 3.6 liters 5.337 moles, and in the end it would produce the 450 grams of magnesium carbonate. Question number 8 is another molarity problem. You've probably recognized by now that a lot of these are either asking for molarity, they're asking for moles, or they're asking for liters. They're all pretty similar once you figure out what they're doing. So let's look at this one. It always gives us pronouns in this book. It never gives people's names. I wish it kind of just made up a name. But anyways, we have a chemist. They're taking 156.7 milliliters of a 1.34 molarity solution of FeCl2, iron chloride. I know, that's just like, sometimes it comes across like you're reading Latin. So I'm just going to write above it what I have here. I have 156.7 milliliters. And I know the molarity of this. I have excess potassium hydroxide, as much as I need. And the question is asking you, what is the mass of this in grams of iron hydroxide? And so you may kind of start to recognize the path that we're going to have to take here to solve this, but I'm asking for grams. And it says I didn't write it down, but it says how much should it produce. And since we just studied actual and theoretical yield, we're going to figure out what the theoretical yield in a perfect world this equation would produce. And so I'm starting here, and I have milliliters and molarity, and I got to get over here to grams. And so first thing is I'm going to figure out moles. Now, usually when we're figuring out moles, we have a grams. But I don't have grams. I have molarity. I can figure out moles from molarity because molarity is moles over liters. So I'm just going to solve in all my information for that. I don't know my moles. Don't forget to convert your milliliters to liters. This book almost always gives you that extra step. So move your decimal point 3 times, 1, 2, 3. And so you have 0.156 liters. And so I'm going to multiply both sides by this. I'm not going to show you the algebra of this step. I'm hoping you can figure that one out on your own. Moles of FeCl2. So now, from moles of one of these guys, I know I can go to moles of here. Just to make sure I show you the path of my thinking here, I'm going from milliliters of iron chloride to moles of iron chloride. From moles of iron chloride, I'm going to moles of iron hydroxide. And from moles of this, I can go to grams. So just another very long, lots of processes, word problems. So I've just calculated this step. Moles of iron chloride. So now from moles of iron chloride, I'm going to go moles to moles. The reason I go moles to moles here is with my balanced equation. This is a really nice one because it's 1 to 1. So I know that if I have 0.210 moles of this, I have 0.210 moles of this, which is kind of nice. Sometimes you actually have to write that out and write out the steps and do the cancellations of the units if it's not a 1-to-1 ratio. So I'm going to take go ahead and pause it and try to figure this part out on your own. Okay, I got a little lazy on this. I know that may bug some people. I'm actually dropping the FeOH2 here because I'm running out of space. But moles of this is going to cancel out with moles on the bottom. And this is my molecular mass that I got from calculating my periodic table, right? I have taken an iron and I've added it to 2 hydroxides and I've gotten 89.87 grams. You should be really good at calculating that by now. And in the end, you end up with, you're going to put into your calculator 0.21 times 89.87. The end result is 18.9 grams. So I went from milliliters to moles to 18.9 grams. For question number 9 of chapter 9 comprehension check, we're actually switching from molarity to molality, which is represented with a little m, and it's done a little bit different. It's moles of solute over kilograms of solvent. And so the first problem, they're super kind. It's really easy. They just ask you to find the molality of something. They say if you dissolve 125 grams of potassium bromide in 750 grams of water, what is the molality? Well, I know molality, the little m, is moles over kilograms. So the first thing we need to know is we need to know the moles of the solute. And so the solute in this is potassium bromide, and it would be too easy if they give us it in moles. So of course they give it to us in grams. So we have 125 grams. So let's stop and take a minute and you pause it and calculate it in moles and come back and check me. So 25 grams of potassium bromide times 1 mole over 119 grams. Where did I get that, guys? Come on, periodic table. And I end up with 1.05 moles of potassium bromide. So I know now my first part of my molality problem. I know my moles. Now the next one asks for kilograms of solvent. And so our solvent for this is water. Water is the universal solvent, meaning most things can dissolve in water. And so it asks for it in kilograms, and they don't give it to you in kilograms. So you're going to have to go from grams to kilograms. We'll refresh King Herod here. King Herod died drinking chocolate milk, meters, liters, grams. So if I use King Herod, I'm going from grams to kilograms. 1, 2, 3. I'm doing 3 hops to the left. And so I'm going to move my decimal point 3 spots to the left, which is how I went from 1, 2, 3. So all you're going to do at this point is do the division. 1.4 is the molality. Question number 10 is another molality question, though it is a little harder to figure out that it's a molality question because it doesn't actually even say that word anywhere in the problem. So let's read it and see if we can figure that out. A chemist needs a solution of SrNO3(2). That's strontium nitrate. That has a concentration of 0.75 molality. Oh, I was wrong. There's the molality. If she uses this many grams of water, how many grams of her compound does she need to use? And so just like molality said earlier, I'm going to need moles of solute over kilograms of solvent. And do I know any of that? I can figure that out. I know that I have 350 grams of water, and that's my solvent. So that can easily be converted by moving my decimal 1, 2, 3 spots. 1, 2, 3 to 0.35 kilograms of water. All right, so now I don't know my moles. I don't have any information that I can calculate moles from. Remember, if I have my periodic table, I can calculate moles from grams and all those types of things, but I don't really have that. But I do have molality. So I'm going to put for here. Put this in for molality. Now, I'm just going to solve through it algebraically to find moles. So I'm going to take 0.35, multiply both sides, multiply this by it. 0.26 moles, and it's moles of this compound, strontium. Lots of polyatomic ions these days. So I know how many moles I need to add, but of course they don't ask for it in moles. They ask how many grams. So you know how to go from moles to grams. We have done this. I'm going to put moles on the bottom and grams on the top. I'm going to look to see though, because I don't want to do the math. All right, to go to moles, I'm going to put moles on the bottom. And I get my 211 from adding up the numbers in my periodic table. Be really careful when you're adding up the masses, especially when you have all these polyatomic ions and things. I would even do it twice to double check because I see on my students a lot of times this is their mistake. And then all the math after that will be wrong, especially if this mistake happens early on. This is just an adding mistake, so double check this, especially when you get these really big, complicated compounds. And in the result, I'm left with 55 grams of the compound. And so basically she needs to mass out this many grams in order to make the solution that she's wanting.